Okay, so let's see where we were at. Be a little easier, I guess. Right, okay. So we were, okay, yeah. We were having this discussion about multiple linear regression and overfitting. So what we're going to do today is we're going to finish this activity, and then we're going to look at a SAS activity on multiple linear regression. Okay. Anybody have any questions before we finish up the activity here? Okay. So overfitting, yeah, overfitting is a easy thing to fall victim to, I guess, when using multiple linear regression, especially when you're newer to regression modeling and predictive modeling. I think this idea of using information to make predictions is exciting and cool. And so it's easy to go overboard and use too much information, too many predictors. But that can result in sets of predictions like this that fit your current data set really well, but don't generalize well outside your data set. Okay. And so R squared, which is the most commonly used metric for evaluating how well a regression model is fitting one's data, always gets bigger when you add more predictors to the model. So that's what makes it easy to, like if one's not careful and just if you have like a very surface level knowledge of regression modeling, you might think that always having an R squared is better. But that's not the case because you can overfit like this if you just rely on R squared. It's what's called a greedy metric. It will always suggest you add more predictors to the model if you base your decision off which model to use. Okay. So we talked about Occam's razor. This idea that you want the simplest model that does a good job of fitting the data. Okay. And this definitely works well in practice. Like, so I've used that rule of thumb. It is tempting, like you have a more complicated model that's taking into account more information. It's almost a little counterintuitive that you would think, well, the more information, the better that we use in our model. But that's not true, and it's held up just like empirically. Like I've talked about how I like to predict college basketball games using regression models or similar predictive models. And there's many different types of models you can consider. And like usually when I do this, I have 10 or so different models. And I always, when I'm like for competitions, when I select my final model, it's this trade-off I'm always like evaluating between like how well is the model fitting the data and how complicated is it? How many predictors does it have? So I often pick the simplest model, the model with the least predictors that's doing like best or second best in fitting the data. And then often what happens is that model does nearly the best for the performance on the future data that hasn't been seen yet. And if I would have picked the more complicated model, that often does worse. So it holds up in real life that going with the simpler model will get you better predictions for the future. And so there's some statistics that can help us select that type of model, a simple model that does well in an objective way. One of which is the adjusted R squared. So it's similar to the regular R squared, but it has an adjustment that lowers this value based on the number of predictors in the model, essentially. Which you can see showing up here because K is the number of predictors in our model. So if you think about this equation and break it down into pieces, it's kind of complicated because there's fractions and fractions, but if you look at it close enough, you'll realize that the more predictors in the model, that can lower the adjusted R squared value just by having K be bigger. Okay. So some things to think about. Is it ever possible to have R squared equal to adjusted R squared? Okay, so we look at the two equations. Okay. I mean, we're going to do a little work on the board maybe for this, so it won't be in the Zoom meeting, but I mean, the short answer, I guess this is just a yes/no question. So it's easier than the next bullet here. So yes, they can be equal. Okay. Be equal in extreme cases. So for example, if SSE equals 0, then what's true about R squared? 0. Yes. SSE is our sum of squared errors. Yeah, so what's true about if all of our errors are 0 essentially? And it'd be 1. This is 1, yeah. And then what do we see? It's a little bit easier to see for the adjusted R squared. If SSE is 0, what is the adjusted R squared? Also 1. So in this extreme case where you perfectly fit your data, the two values would be both 1. So it is possible to have them be equal. So since this was just a yes/no question, it's yes. Yes, they can be equal. We found an example that's possible. But more importantly, that's very often not the case. It's not usually the case that you have an R squared of 1 or that your errors are all 0. That would correspond to like this case where you're perfectly fitting all the data points with the green line. Okay. What is always true regarding the relationship? Okay, so yeah, this one takes a bit more math. Okay, so apologies to whoever's in the Zoom meeting. R squared equals SS mod over SS total. And then adjusted R squared is SSE n minus k minus 1 over SS total over n minus 1. Okay. write too big. I lost room already. Okay, so then what we can do, okay, so they both got SS total, so that makes them a little easier to compare. There'd be a lot of ways you could go about finding some inequality between these two. If we have SF total, we like that because that makes it easier to compare them. But this SF model is in the regular R squared, but not in the other equation. And then similarly, SSE is in here, but not in the other one. So what could we do to make it more comparable here? Now it's early. But
you can multiply with the numerator. Like 5 each of them equal to each other, multiply by the numerator.
yeah, you could do something like that for sure. To get them a common denominator. Yeah. Yeah, sure. Let's do that. Okay, so yeah, to get a common denominator here. We've got SS total over n minus 1. That's one way we could do that. And now they have a common denominator. So yeah, that's I like that. Okay, that's actually easier than what I was thinking. So okay, so now the denominators are the same, right? So if we have R squared and the adjusted R squared on both sides, okay. SS total, as long as your points aren't all the same exact value for your entire data set, SF total is always going to be positive. So we can assume that that's the case, that we don't have the response values the same for every single data point. We'll just assume that here. So then if we have then if we have R squared, let's see. Do this. Okay. So, and my math's a little bit rusty. I'm trying to think about how you can do this. Okay, so we can substitute in adjusted R squared into the equation up here. Okay, so what we're going to do is, okay, this is true. So we have SS model divided by n minus 1 over SS total over n minus 1. Okay, and we already have the denominators the same. Let's get it to look like the adjusted R squared. So what we can do is then we'll pull this term out a little bit. So it's 1 over n minus 1, just like that. Okay, and then divide by n minus k minus 1, but then also times n minus k minus 1. Okay, so that's still equal. So it's like a well-chosen one is what they like to call this in statistics. We're multiplying by this and this. Yeah. Did I copy the equation down correctly? SS model over SS total. Yeah. Okay. Okay. Because now what's nice is we have this term. This term. What is this term in the equation now? The adjusted R squared. Yep. So now that makes them easier to compare. As we have R squared, we have an equation relating the two now. R squared equals adjusted R squared times this factor. Right. Times n minus k minus 1 over n minus 1. Okay. And what do we know is true about n minus k minus 1 over n minus 1?
It'd be less than one, the value.
Yeah, it's going to be less than 1. Okay. So this is always positive because we can't have more predictors than our sample size. So this term, we'll call it like S star. Okay. This term S star is I think it's P0. I don't think so, but anyway, it has to be less than or equal to 1. And if we assume we have at least one predictor, I think it has to be less than 1. Yeah. Okay, that's less than 1. So what we end up with I'm supposed to have less than or equal to. Okay. Then yeah, I guess that implies this r squared equals the adjusted r squared times s r. And we know that S star is less than 1. Did I do that right?
So R squared will always be less than R squared adjusted.
Yeah, which is not true. So I'm wondering what I did wrong. Did I have stuff on the wrong side of the equation? What did I do wrong? Maybe I'll have to think about that because I did something wrong. I didn't show something that's true. Okay. I'll have to think about that last part. I mean, what I'm supposed to be showing that I'm having trouble showing right now for some reason is that that the r squared, nope. R squared is always greater than or equal to. Gotta brush up on my math skills. So I guess I'll talk about that next class, start of next class, I suppose. So that's always true. Right. And then we were considering this quadratic model here. Yeah, it's been a little bit. We were modeling the wave heights using the wind speeds. And we were considering, did we need a quadratic term in the model or not? Okay. We can have SAS calculate the adjusted R squared for the quadratic model, which is the biggest model here. And then it reduces the number of predictors one by one and gives you the adjusted R squared for each of those automatically. Okay. And simply what you do is pick the model with the largest R squared, adjusted R squared. So in this case, that favors the quadratic model. It wants the biggest model with this quadratic term in here because it had the largest adjusted R squared. So since the quadratic model has the largest adjusted R squared value, we select this as our final model. Okay. And that was the last bullet. So like I said, I'll review my math skills to show how this inequality is true next time. But that was it for the multiple linear regression activity. So that introduced us to all the concepts we'll cover for multiple linear regression. And now today we'll spend time working on a SAS activity, learning about SAS coding. Yeah. Yeah. Oh, the very last bullet here. Okay. So go ahead and get SAS activity 6 open. Yeah. And we'll look at coding up a multiple linear regression model and related things. Oh, I see what I did wrong. Okay. This is SSE in the numerator here for the adjusted R squared. This was SF model, so it's not the same term. So I couldn't substitute it in like that. Okay, that was not the adjusted R squared. That's why. Through that point, so that was the mistake. Okay. Anybody else need to say anything on the activity before we look at SAS activity 6? Okay. So for SAS activity 6, we're going to be looking at this, continuing with this data set on the Great Lakes again, collected from the buoys. We're going to be looking at using multiple linear regression now to model this data. Okay, so go ahead and get SAS Studio open. Save a new file. Okay. Going to do the same thing we've done before, where we import it into a data set called Great Lakes. All right, so you could go through the import wizard by finding it over here again, the data file, and my shared file links. You open that up and go to the Great Lakes data like this. You could import it using the import wizard. I'm going to kind of skip over that a little bit by just this. Okay. That allows us to import the data like that. Okay. I think we did this in a previous SAS activity, maybe importing this data. So you might be able to find it in one of the old ones, but if you do use the import wizard, remember we need to add this replace option, this guessing rows equals max option, and then update the out statement with a new data set name. Then once you have the code, make sure you run it and see that you can look at the data and make sure it looks reasonable. Hear a lot of clicking still, so I'll wait a little bit, make sure everyone imports the data before we get going. I guess maybe while people are doing that, let's print the first 10 rows. Okay, so we can use a proc print. Big enough for people to see in the back. Okay. Anybody have any trouble importing the data? Yeah. Cool.
Oh, okay. Everything looks good. I think just the out statement. Oh, okay. Yeah.
Oh, and then we'll get rid of the data too.
Oh.
And that should, I think that should.
Oh.
All right. So yeah, we print the first few rows. Okay, so in this data set, this is how it came directly from the Great Lakes Observing System. So they named the variables in such a way that they have what we call special characters. There's parentheses in the variable names, right? And also this degree symbol, which SAS doesn't like. So what we can do is rename them to be variable names that play a little bit nicer with SAS. Okay. So what we're gonna do is rename them in what's called a data step. Okay, so we say data, and we'll call it maybe like Great Lakes new. We'll say it place like that. Set Great Lakes. Okay. So what this code does is we're creating a new data set, a new SAS data set called Great Lakes New, and we're starting with an exact duplicate or copy of the Great Lakes data set that we just imported. And we're going to fix up those column names. Okay. So you could call it like Great Lakes New, or sometimes like I call these types of data sets when I make them like Great Lakes Clean, because it's a clean data set now. Okay. You can do either one. And then to fix up those column names, one way to do it is to use a rename statement. So we say rename, and then the general syntax of the rename statement is like old variable name equals, bless you, equals new variable name. Just like that. And you can do it with, it's like old variable name 1 equals the new variable for the name for the first one. And then if you want another one, this is one of those cases where SAS does not have like a semicolon for each of them. You just get one semicolon for all the columns you want to rename, and you just keep adding lines like this. Okay. So this is the general syntax, but we're going to do it for this data set. So if we look at like the results, okay, the first variable we're going to rename is the time variable. Okay. I would suggest, like when I do this, to make sure you get the spelling exactly right, I think it's good to look at the proc print output and just manually copy the variable name rather than looking at it, because the spaces matter in the case, I believe, as well. So old variable name. So you would think we would do it like this. The problem is with SAS is that when there's special characters like this, SAS gets messed up by the space. It thinks like we're starting something new. It doesn't think it's still the variable name here. So we have to like enclose the whole variable name such that it keeps reading it as a single entity, I guess. And we can do that with a single parenthesis on each side that like encloses that variable name so that it tells SAS, hey, this is the whole thing is the variable name. And then we do a lowercase n, and it should turn teal if we did it properly like this. Okay. So this is how you can refer, using this syntax, is how you can refer to SAS variable names that have special characters in them. So this is the old variable name that's, this is what's annoying about it. If we ever wanted to refer to this variable in procs, we would have to do it this way, but we're going to call it just time so that it's a little bit less work for us later. Or sometimes maybe you want to rename the variable name to be more descriptive, in which case you can do that as well. All right. The other ones we wanted to rename. Okay, the degree symbols. Oof. So next we'll rename the water variable. Okay, this is one that I would highly recommend copying it directly from the proc print output, because there's this degree symbol. It's really hard to match that correctly because I don't even think there's a way to type that on your keyboard. And if you Google like degree symbol, there's slightly different degree symbols that won't match it. So it's hard to find exactly which one you need. So that's why I just recommend copying it from here. And then it's like this, that, and then we're going to call that temp F for temperature in Fahrenheit. Okay, and then for the next ones, we're also going to rename the wind variable and the waves variable. And so we'll add a couple more rows like that. And so for wind, we do the same thing. Highlight that and copy that exactly. Okay, yeah, and sometimes it copies over extra space like that. We don't want that. We're just going to call that wind speed. And then the waves also has special characters. And then we'll fix that up.
Do we need the commas after?
No, there should not be commas, sorry. There we go. Yeah, thanks. And then we're going to call the last one wave height. There we go. That should run. Okay. So this is a little bit of what we'd call data cleaning. Unfortunately, as a statistician or a data scientist, I think people estimate you spend like 70 to 80% of your time just cleaning the data and not actually analyzing it. Like doing things like this, renaming the columns, transposing, reorienting the data set in a proper way for analysis, things like that, which we don't really go over those skills in this class, but you would learn it in like Stat 318. You learn SAS programming to do data cleaning. Or Stat 418 is the class I teach that's doing that in R programming, a lot of data cleaning and operations like that. Right, this step historically has always given people a lot of issues. Is anybody having an error or problems here with this? Yeah, okay.
Still showing like in the data set, doesn't change.
Yeah, I didn't actually rename it. Okay, yeah, let's look at the waves. See. And is the output data in the Great Lakes unique? Oh, okay, yeah, that's the thing. Yeah, let's look at that. Yeah. Perfect.
Yeah, so when we have like multiple data sets that we're working with now in the viewer, SAS has it like You can look at this drop down. And maybe we don't want the replace there. We don't want that actually. Yeah, there we go. So you should be able to see, opening up the Great Lakes clean data set, the variable names are now don't have the special characters like they did before. And I got rid of this replace option here. I think it runs fine either way, but okay. All right, so that was a little bit of data cleaning real quick. Then for part C, okay, let's use proc core. And we just want the variables temperature, wind speed, and wave height. And so we're going to do this. We do Great Lakes clean. And if we run this by default without specifying a var statement, it just gives it for all the quantitative variables, which is more than we want. We don't want date and time. So we can subset the variables that it does this operation for using a var statement. So we're just going to say yeah, temp, wind speed, and wave height. Okay, so temp. Wind speed and wave height, like that. And if we run that, we get this output here. Okay. And which variables have the strongest positive correlation? Part D. Okay, so based on this output, which two variables have the strongest positive correlation?
Wave height and wind speed.
Yeah, wave height and wind speed. So right here has a correlation of almost 0.7. Okay. So the format in the cells here, as a reminder, it's giving the correlation coefficient between the two variables here. So it's like, this is the correlation between wind speed and temperature. It's like the cross section of those two. It gives the p-value for testing if that correlation is truly 0 or not, which we haven't really concerned ourselves with in this class, but it's a thing some people do. And then it gives the sample size that was used to calculate that correlation. Okay, because there's some missing values in this data set. If we look at, oh, how can we open it up? Oh yeah, in libraries. We open up the data set actually. You can see that there are some missing values, for example, right, in the wave heights. Okay, so SAS codes missing values as just a decimal, a period character. And so, for example, when you're calculating the correlation between, say, wind speed and wave height, it's based on the pairwise observations. So like when there's a missing value for wave height for that row, that entire row gets excluded from the calculation of the correlation coefficient. You need what's called pairwise complete observations in the calculation of it. So this row is also excluded. They're both missing. These two rows are thrown out in that calculation. So that's how you can end up with actually different different number of observations for each variable that were used to calculate those correlations. Okay. So in this case, yeah, we said wave height and wind speed. Okay. Now we'll make a scatter plot for those two variables using proc sgplot. So we'll do proc sgplot data equals Great Lakes clean. And then we say okay, so to get just the points, we use scatter x equals y equals, and we say our x and y variables. So in this case, if we're modeling wave heights and wind speeds, what is our response variable? Probably wave height. Yeah, that's what's affected by the wind speeds. It wouldn't really be the other way around.
Right, yes, line 21 will change that to clean rather than having. Okay, I think that should get a favor on everything. Yeah, just like that. I think if we is that here?
Yeah. I'm supposed to get.
Does it say it doesn't exist?
Yeah.
Yeah, okay. Yeah, let's look at the code. Well, let's get rid of that replace option, would be line 21.
Oh, good.
And then rerun the whole thing. Let's see if that. Oh, okay, let's look at the code, but it can't find those various forms.
Let's see.
What happens if we run lines 27 to 25?
seems like a very.
Oh, okay. That variable. Oh, okay. So yeah, let's look at the code again. So it was saying it doesn't recognize those variable names.
Okay.
Is what it, the ones on the left actually, yeah. But that was the problem. Which often means they're just like misspelled, they're not matched exactly. And I think looking at them, I think
So
it's
maybe
like there's a space before the left parentheses of each, and I think we need to add.
Oh, it's like right here.
Yeah, that's what it. See if it still gives that warning or not. That looks a lot better. So now
Thank you.
yeah.
So we say y is wave height, x is wind speed. Okay. And SAS is case agnostic with the variable names again. So you'll notice I'm doing it like all lowercase here, and that's fine. We can add labels. So we'll say like x-axis, or maybe just to show what this looks like just with this. Okay. This will give you a scatter plot. Okay, like this, but it just says wind speed and wave height. Maybe we do want to show the labels now. So we would say x-axis label equals like that. And then that'll update the labels on the axes, which is good to do. And then we can also update the title. I can say like Great Lakes data, something like this. Okay. And I always like to show this now because I think it's really helpful. Like, again, if I was like doing this on my own and didn't have someone else showing me how to do it, you know, what I would enter to get this code in ChatGPT, create a scatter plot using proc-sgplot and SAS. That's what I would say. And then it, yeah, did a really good job giving the right code for that, which makes it easy to copy and saves you time a little bit. All right. So this makes a scatter plot, but there's not a line of best fit through it, right? But I asked for this with the least squares regression line, right? So we can then, to get that, we just modify the code to, instead of saying scatter for scatter plot, we do reg for regression. And that plots the same thing with the points, but now it adds a simple linear regression line to the plot. Okay. Right. And you'll notice in here, the SAS developers very purposely, okay, so not all software does this. I think I'm pretty critical of SAS sometimes, but this is good that they do this. You'll notice that the regression line starts right at the smallest value in the data set, and it goes up until the biggest observed X value. Okay. And That's because the developers knew that outside that range is extrapolation, you shouldn't get predicted values. And so they drew it very purposely to not go infinitely in each direction, because the only place to get appropriate predictions is where they drew the line. Okay, so that was 1E. For 2A, we're going to fit a linear regression model. And so to do that, there is a proc reg, which is sort of like the older procedure, in my opinion. I think, people use it. It does have some nice features specifically for linear regression. The thing is, if you want to fit like an ANOVA model or other types of what are called generalized linear models, like a logistic regression model, you cannot do that with ProcReg. ProcReg is very specifically made for just linear regression. But if you go on into using SAS more, like for your job, it's very likely you would need potentially other types of models as well. So I like to teach ProcGLM instead, because it's a much more general procedure that can be used for modeling. But just know that you might see ProcReg, and that's effectively doing the same thing. But I think it's good to just get in the habit of knowing how to use ProcGLM. Okay. So we're going to use ProcGLM. Whenever you have ProcGLM, you need to specify your model that you're doing. So that's of the form response variable equals explanatory variable. Actually, you have like explanatory variables. In this case, we're going to have wave height, and our explanatory variable is wind speed, right? So this will fit a model. Gives you the line of best fit through the points, the regression output, the ANOVA table. But we also wanted to get confidence intervals for the intercept and slope, and also diagnostic plots here. So to get diagnostic plots, we add in the first line here in the ProcGLM statement, we add plots equals diagnostics, just like this. And this will add that 3x3 grid of plots, which we use to check the model assumptions. Okay. Should be blue. So make sure there's just the one semicolon for this whole line. Now we can see that 3x3 grid of diagnostic plots showing up. Okay. All right. And then we also wanted to get confidence intervals. So to do that, we add this slash after the model statement, and we say CL harm, which stands for confidence limits parameters. Feels like it should be like param rather than parm, but I guess that's what they chose to do. So this by default gives 95% confidence intervals because of that whole 0.05 tendency to be the default in statistics has to do with that. You can get different levels of confidence for these by specifying an alpha option. So alpha equals 0.05 corresponds to 95% confidence intervals, which is the default anyways. But you could get, say, a 99% confidence interval by doing this. by changing it to 0.01. We're just going to keep it at 95%. Like that. And then we got 95% confidence intervals for the intercept and for the slope here. Okay. So let's see what I asked for in the activity. Oh, okay, interpreting things. All right, so this is still just a simple linear regression model, but here we'll look at, providing the intercept value and interpreting it in context with the units of measurement. Okay, so we'll do that real quick. Oops. We'll say the estimated intercept. So what's our estimated intercept based on this output here?
0.03.
Yeah, about 0.03 right here. So this table gives you all the numbers you need to write out your estimated regression equation. Right? The estimated intercept is this, which means that, and how could we interpret this value here knowing that we're modeling the wave heights using the wind speed? What does this intercept represent? Right, yeah, exactly. So this is the expected, and it's important to say expected or average wind speed. Or, I'm sorry, wave height. When the wind speed is 0 knots, which is the way the conversion works is also 0 miles per hour. Too much info. We just want to know what the conversion is real quick. Okay. Yeah, so knots is like, yeah, the conversion is very simple actually. It's you just multiply speed in knots by that much and you get the miles per hour. So it's very direct conversion. It's nearly the same. Okay, so 2B, I asked for. Yep, okay, so you can also interpret the slope for 2C. Okay, so the estimated slope is, so what's our estimated slope from this output? Right, yeah, the 0.19 value here, right in the bottom. So all the beta hats are always in this estimate column again, and it'll say parameter, it will always say intercept for every single model that you have an intercept in, which we'll always have in this class. And then it'll say your predictor variable name, the X rate. So that is our beta hat 1. So the estimated slope is this, which means that, does anybody want to interpret this for us?
For every 1 knot increase in wind speed, the wave height increases by 0.19 feet.
Which means that for every 1 knot increase in wind speed. Yeah. The peak wave height increases by 0.199 feet. And then what do we need to add to this? Yeah, it's the right idea. For the phrasing, we'll say it increases by this much on average, right? Okay. It seems like maybe that's not important if it's left off, but it's just a matter of like being technically correct with the language, I guess, because it's not that it's always the case that as the wind speed goes up by this much, the wave heights don't like raise by that much exactly all the time. It's just on average across many waves. That's the trend that we see. So it's kind of an important distinction, I guess. Like in another example, it would be like, if we were looking at high school GPAs of students and college GPAs, maybe for every 1/10 higher a student's high school GPA is, their college GPA is 1/10 point higher on average. But there's exceptions. There's individual students where they have like higher GPAs, but lower college GPAs or vice versa. So it's just on average trend across the data set that we observed. Yeah.
So for 2B, intercept, we have values that are pretty close to 0, but would that still be considered extrapolation?
Oh, that's a good point. Right, technically. Oh, actually, you know what? I think we do have, it is really close. I think if we look at the data sets. Oh yeah, we can open it up over here. I think if we look at the data set, we do have some. I don't know if it allows us to sort. Yeah, it does. Oh, you're right. No, we don't have values that are exactly 0 for the wind speed. So yeah, technically that's extrapolation. You're right. That's a good point to add here. I'll add that as like an aside. So like technically, 0 is outside the range of the data set. So this is extrapolation. So this is, we'll say like by definition, extrapolation. Yeah, great point. Yeah, it's always a trade-off of essentially it's like, can we assume, given what we saw, can we assume that the straight line pattern continues outside the range of the observed values? So we can't necessarily assume that, right? Yeah. But here it is really close, but definitely still technically extrapolation. Yeah, for sure. Okay, now a confidence interval for the slope, which we have not covered yet. Okay. So for the confidence interval, I think I said for the slope. Yeah. Okay, I'll give a blueprint interpretation here. So if we look at like the blueprint interpretation for the slope, let's go to simple linear regression. I don't think I give the, yeah, not for a confidence interval. Okay. It's our blueprint interpretation. we're just interpreting the slope, which I think is a good starting point when trying to interpret a confidence interval for a slope. Okay. And then I'll write out the blueprint interpretation for confidence interval for the slope here. Okay. So we tweak it a little bit by pretty much saying we are, for example, 95%. So this would be for a 95% CI, although you could have different levels of confidence. We're 95% confident that and then the slope interpretation, pretty much. So every 1 unit increase in X, we expect Y to increase by between lower bound and upper bound. On average. So that's a blueprint confidence interpretation of a confidence interval for a slope. So we'll take this here and do it for this problem in particular. Okay, so first let's get our lower bound and our upper bound values from the output. Okay. That'll probably be the last thing that we do. So the lower bound and upper bound values are, we look in the same table where we get the estimates themselves, and then we have the lower bound in the 95% confidence limits part right there. We have lower bound, comma, upper bound. Okay, notice this is for the slope. And we can round these values down to like 2 or 3 decimal places. We'll say 2 here. So we are 95% confident that for every 1 unit increase in X. Okay, maybe we can finish this real quick. That Y will increase, we say, since the slope is positive, by between 0.15 and 0.24. Okay. And then instead of 1 unit increase in X, what should we say for this problem here? Yeah, 1 knot increase in wind speed. So for every 1 knot increase in wind speed, we expect, yeah, the peak wave height to increase by between blank and blank. And then instead of units, we can say feet. So that's how we can interpret the confidence interval for the slope here. Very similar to the interpretation of just the slope itself, but a little bit of extra wording in there. All right, so make sure to save your SAS activity, and then we only have a little bit more in this. Yeah, just a few more parts that we'll finish up next time. Okay.